Morning, everyone. Thank you very much for joining our webinar today. So today we're joined by Dr. Joe Wolfenden, who is part of the Quasar Group at the University of Liverpool. So today he's going to give us a talk on precision without perturbation, non-invasive diagnostics for plasma accelerators. So just a few housekeeping rules. If you would like to ask a question, then you're more than welcome to. If you could please use the Q&A function to do that, that would be great. We'll collect all the questions and then we'll put them to Joe at the end. So I hope you enjoy the seminar and thanks very much. Over to you, Joe.
Hi everyone. Thank you for that introduction. Yes, I'm Joseph Wolfenden, and I'm going to be talking to you today about non-invasive diagnostics for plasma accelerators. So here we go. So just going to give you an overview of what we're discussing today. You'll have to forgive me if the first few slides are sort of setting out my stall are a bit wordy, but I really need to go through why we're measuring these things and why. Measuring versus monitoring, because there's a subtle difference there and it is important. It makes a big difference in terms of how we build and operate these pieces of instrumentation. What exactly we mean by non-invasive, because it seems like it's straightforward, but it can be quite tricky. The diagnostic problems that we will run into with plasma accelerators and what are the causes of those. And then finally, I've got a couple of examples to go through where we look at standard instrumentation, why it doesn't work, and how people are working on new types of diagnostics to solve these issues. So to begin with, what are we measuring and why? So from a mathematical point of view, a particle beam or a bunch of particles is a 60 phase space of n particles. So if in theory you have three bunches, they look like this, they're grouped together, and you can take a snapshot of their properties in space and time, and that's it, you know what they look like. But in reality, what happens is as soon as these bunches start to move, they go all over the place. This is where the 60 phase space comes into play. It's not a simple thing to do, and there's lots of projections that we're able to measure. Obviously, there's no such thing as like a 60 phase space myometer. So we are doing looking at correlations and how these interact. So what are we commonly looking for when we're measuring properties of a particle bunch? I've said commonly because really depending on what sort of accelerator you have, whether you have a synchrotron, a LINAC, cyclotron, you've got different parameters there, but broadly speaking, for a bunch, we're going to be interested in these sort of properties. So the first one is transverse position and then propagation angle. So when I say transverse, I mean we have a bunch propagating along a beam pipe. If we were to take a slice along that beam pipe, transverse is transverse to that motion along the beam pipe. So you've got x and x prime is the where is it and in what how is that varying with time? Is it drifting left, right? Is it drifting up and down? That sort of thing. So yeah, where is the beam and where is it going? Then we have sort of, if you think the second order moment of these, so you have the transverse size and the divergence. So that's how big is the beam and how is it spreading as well. Then we have transverse admittance, which is a combination of the above, which is a measure of how big the beam is within the projection of the phase space that you're looking at. So I've got epsilon x there, that would be in the x prime projection of the 60 phase space. How big is the beam? What volume does the beam take up in that phase space? And it is generally a measure of beam quality. No matter what your application of the beam is, you tend to have parameters like luminosity, brightness, things like this. Emitters fits into all of these, and it really does depend. It really does make a big difference on how well your accelerator operates. Then we have energy, which is sort of self-explanatory. Then we also have energy spread and the bunch length. So you can see this is like the longitudinal equivalent of the size. So it's how long is the bunch. How long is the bunch, the energy of the bunch, and then also how is this changing? If you have a spread of energies within a bunch, they will take different paths as they go through your accelerator. And that means that some particles will catch up with others, some will slow down and fall behind, and it means it will change the overall length of the bunch as it goes around. And then finally, we have charge, which is how much beam there's there, but also how much beam has been lost as well. That's really important to know in terms of machine protection, in terms of background for the measurements that the beam has been used for, in terms of activating components of your accelerator, which means that maintenance becomes difficult longer term. If you have a very high power accelerator, you could also burn holes in your beam pipe if you're not careful. So yeah, there's a whole zoo of things here, and we are interested in measuring all of them. So I've just used that word measuring there. And what do we mean by measuring? So often we're targeting a very precise result, and it may take multiple data points to achieve this result, but the whole point is this precision and accuracy. Invasiveness, which I'll come on to. So what I mean by here is that the beam can be destroyed in the process. It's not a problem as long as we get that measurement. The measurement is the end goal. The whole reason the beam is being turned on and being run is to achieve that measurement. So monitoring, you have this subtle difference. Precision may not be as important. You're targeting single shot or bunch by bunch measurements. You don't want to be accumulating averages. You want to know exactly what the beam looks like in that moment. And non-invasiveness is a rule. By definition, these things need to be non-invasive. The beam can then be applied to something else. And it's that application which is the end goal. You're taking some readings of the beam and then using it to supply it to a patient for treatment, to send it to an undulator to produce FEL radiation, to send to a collider. So you really don't want to be perturbing that beam. So non-invasive, if someone says, what does a non-invasive diagnostic look like? That's quite a difficult question to answer as soon as you start to think about it, because there is no one size fits all answer. It really is application specific. So I've got an example to try and draw a line with this. Something called diffraction radiation. The specifics of it don't matter right now, but essentially what happens is you have some sort of aperture. So this is a slit here, this is a metallic slit, and you have, in this case, an electron passing through the center of the slit. The electric field of the electron, if it's high enough energy, will produce radiation which is emitted from the sides of the slit. And then you can take measurements of that radiation and infer properties of the bunch. The beam itself is not interacting with the slit, it's going straight through the center. So you think, great, non-invasive. And some measurements were taken at INFN in about 2011. So I'll just, as a note here, in a lot of these slides, I have references noted at the corner here. They're at the end. So please do take a look if you're interested in any of these specific results. I'm really going to be giving like a high level overview of them. So we have this nice interference pattern here. They were actually using two slits to produce a diffraction radiation interferometry. But you can see you get a really nice pattern here, and they were able to measure things like the beam size, the divergence, the admittance. It really worked very well. So then a few years ago, people thought, well, it works on a LINAC, why wouldn't it work on a storage ring? So I think this was at Cornell, they applied the same thing, and you get the same result. It looks great. So yeah, that means it's non-invasive. However, the beam lifetime in the storage ring dropped by an order of magnitude. It went from being about 20 minutes per fill to needing 2 or 3 minutes. So very much not non-invasive. The problem was that the beam was being perturbed as it passed through the slit, but for the applications on the LINAC, that perturbation was so small that you could then still use the beam. But in a storage ring, that perturbation accumulated as it passed through and passed through and passed through, and it slowly degraded the beam, and you end up losing the beam. The beam lifetime was gone. So when you're talking about non-invasive, it's really, really application specific. Some accelerators will tolerate certain types of diagnostics, others won't. So there is, like I said, there's no one size fits all answer. So why do plasma accelerators cause us a problem, and why do we need to start looking at these non-invasive solutions? it really comes down to the parameters of the beams that are being produced. So we have micrometer scale transverse profiles. A lot of the screens that we use, things like scintillation screens, the resolution on a scintillation screen is dictated by the crystal sizes. And as soon as you start getting to the micrometer scale, you're getting on the scale of the crystals themselves, and you get like a blooming effect, which means you can't see the beam. Things like other sources of radiation, you're getting down to the resolution limit of what's achievable for standard diagnostics. Similar thing with the divergence is millirad scale. In terms of actually taking the measurements, these two are not too different. Combining those two together, you end up with micrometer scale transverse emittance, which again is its own problem. We have longitudinal profiles, which are typically, well, always less than 100 femtoseconds, but also sub-femtoseconds into the attosecond level. This causes all sorts of issues in terms of resolution for existing diagnostics. They just don't work at those sort of timescales. We have this relatively high energy spread, so I've given 5% here as an average, but it can be anything up to 20. The problem with this is it's not a direct issue, it's that a lot of the measurements that we take for other parameters are assuming a low energy spread. The standard instrumentation just by default assumes a low energy spread, because that's true for most standard accelerators. As soon as you start to have any sort of appreciable energy spread, those assumptions fail and the measurements that you take start to not work. And then finally, we have this huge bunch charge range from some applications that you gain nanocoulombs per bunch, a few tens of femtocoulombs. This is really application specific, but it means that a nanocoulomb bunch that can be, if that's coming at a quite high repetition rate, you struggle to put screens in front of that because you're going to start to damage the screens. If you have femtocoulombs of charge, you're going to struggle to actually even produce enough signal to take the measurement in the first place. So I've outlined some challenges here. There's a lot of others, but I think these are the most common amongst the different types of accelerators. And I'm just going to pick two of these to go through some examples. So that is transverse emittance and the longitudinal profile, because these are sort of big ticket items, if you like. The transverse emittance, as I said before, is the profile and the divergence. These are being measured in a combination to produce a transverse emittance. So you sort of have 3 problems to solve with the emittance. And then the longitudinal profile, just the timescales involved are very difficult to get past. So standard methods for transverse emittance, they are heavily reliant on profile measurements, on most, if not all of them. And generally what we mean by this is that we're using a beam to generate some sort of radiation. And then we're hoping that the properties of the beam have been imprinted or mapped onto the radiation properties. So if we can measure the radiation properties, we can measure the beam properties. So a few common examples, I've already mentioned scintillation. So that's, if for anyone doesn't know, the charged particle, in this case an electron, goes through the scintillation material and the material scintillates. It's a uniform distribution produced. It's like you have no angular information from the bunch being imparted onto the light, but you do get very good signal intensity and you get very good spatial resolution as well, down to this micrometer scales I was talking about. You then have transition radiation, which looks very similar, but the screen is different. In this case, it's a metallic screen or a foil. And as the charge goes through this change in dielectric constant, it produces this transition radiation. The charge of the bunch produces an image charge on the screen, which then radiates, and you get this very strange angular distribution, which is characteristic of transition radiation. This is a slice, if you like, so this should look like a ring if you were to image it. And it follows the path, it co-propagates with the beam path in the forward direction, and you can rotate the screen because the backward path follows the angle of specular reflection. So you can actually use this to extract the radiation, which is often what's often done. The problem with this is that the signal level is very, very low. It's something like 1 in 100 particles will radiate. and it's a very low intensity signal. So like one particle produces one photon sort of thing. Whereas with the scintillation, you can get multiple photons from a single electron. And then finally, just in these three examples, there's lots of other examples. I'm looking at synchrotron radiation. So that is charged particle being bent in a magnetic field. It produces synchrotron radiation as it goes around that corner. I've shown this as a very narrow lobe here, where it actually is a line distribution. It gets swept out as it goes through here. Synchrotron radiation, transition radiation are broadband sources. So that means that you're getting all radiation types from X-rays down to up to gigahertz, but the intensity will obviously be different. You're not going to get a lot of X-rays for very low energies, if any. Synchrotron radiation, scintillation comes from the properties of the material. So it is like often a very narrow bandwidth around a particular wavelength, depending on the material that's used. So what do these things look like? If you look at them side by side, they sort of look the same. As soon as you get past the specifics of the generation of the mechanism, it's light at the end of the day, and you're imaging light. So this is an example of a scintillation image, which was taken at Clara, 90 micrometer beam size, 100 picocoulombs. You can see it's something similar at clear, but we've had to use way more charge to produce a sort of similar signal level. And then we have a measurement at diamond. I'm not entirely sure what the bunch charge was. This, because of the repetition rate of the machine, it was a lot of bunches that produced this. And you can see that you've got a really clear image. Because of the extraction method of the synchrotron radiation, you basically have a half mirror. You get this diffraction tail. But other than that, you've got a very easy way of taking profile measurements. You can see that they all have the different challenges in terms of like the transition radiation. You've got a lot of background here because the signal level is so low, and then you've got the diffraction problems here in synchrotron radiation. So as I said, there's many other methods to do this, but I'm just picking out those three because they're quite common, and they're used in many other types of diagnostics, not just transverse emittance. So you take your image of your beam here. First thing you can do is you can take the centroid, and that gives you the position. And that's what was done for the first beam on the LHC. They were using a screen to steer the beam around the first turn. You can then take the width of the distribution, that's fit a Gaussian. If that's applicable, you can do second order moment, whatever you need to do, and you can get the width. You can then vary that width. I'll go into this, how these scans work. But you can basically calculate the emittance by seeing how the width varies. If you send it through a dispersive element like a dipole, you can measure the energy as well, the energy spread. So there's lots of different ways, but so screens are really like a workhorse of most accelerators. So back to emittance, the most common method of calculating emittance, and it's sort of like the standard method of doing it, is a quadrupole scan. And this can be achieved in two ways. You can either use a multi-screen setup, and the basis is you have a quadrupole, you send your beam through it, produce a waste, and then you'll have a screen. And no one has this many screens, but I'm just trying to illustrate the point. You have screens at different positions along that beam envelope. That means you're sampling different points of the phase space, and these are known distances, and you can calculate the emittance. This is quite impractical. Like I said, people don't tend to have that many screens. So what's normally done is a multi-current method. So you have a single quadrupole, you send it through a waste, and you have a single screen, and then you vary the current on that quadrupole to move the position of the waste and change the position of the phase space that you're sampling. So this multi-current method is what I'm going to talk about now. So you vary the current on the quadrupole, you take your profile measurement, and you can plot the width of the beam against the strength of the quadrupole, and you end up with something that looks like this, hopefully. And basically, you can use the beam optics. I'm not going to go through the specifics of the mathematics here, just to give you a flavor of what it looks like. You need to know what your optics are. You need to know how the beam has travelled from wherever you're trying to reconstruct it. So in this case, I would be trying to reconstruct it from the entrance to the quadrupole. So you have a quadrupole beam matrix and you have a drift beam matrix, and measurements of the screen can then be back propagated to the quadrupole. But people do this for a whole beam line. So you'll have a transfer matrix, which is a whole beam line, and you can calculate what the emittance is at the entrance of the beam line itself. And then, yeah, basically you end up with the determinant of the beam matrix, the sigma matrix, and it gives you the emittance. So I'll talk about what these things are in a second. This is just one particular way of fitting it. You end up with the 3 parameters. So this is basically a measure of the beam width. This is a measure, the transverse profile, say the width of the transverse profile. This is a measure of the divergence, which is the width of the angular profile. And you have this correlation term, and that's really why you need to do the scan over the full range to measure this correlation term. And this is how the spatial properties of the bunch map to the angular properties. So it might be, for example, that you have a core of the beam which has less divergence than the halo, or some variation on that. And then basically you can combine these different parameters and produce this epsilon, this emittance. So that works great in most cases. So why doesn't it work for plasma accelerators? There's 2 main limiting factors here. The first one is that it needs multiple measurements, and that means inherently you need beam stability. That means that you can't have the emittance of the beam varying from shot to shot. You can't have the beam size varying too much as you are moving through. So the position of the waist needs to stay stable. And that is difficult to achieve in a plasma accelerator. And even if you have achieved it, it's difficult to verify. The other big thing is the energy spread, as I mentioned before, that starts to creep in. As soon as you end up with anything above the percentage level, what actually happens is that the focusing of the quadrupole is not the same across the whole bunch. So different parts of the beam will have different energies, which means that they will get focused by different amounts. And this epsilon naught, this is the emittance that we want. What happens is you get this additional factor here, which is dependent on the energy spread. So you can't ever measure what the true emittance is because you have this huge energy spread. So how do we do this in plasma accelerators then? There's a few different ways that people have been looking at. One is to try and make use of this energy spread, and that's something called a butterfly method. And what is being done is it uses a large energy spread to produce what's essentially a single shot quadrupole scan. So your beamline will look something like this. You'll still have your quadrupoles and it will still be focusing the beam to a waist. Before it reaches that waist, you send it through a dipole. And then you end up with your waist here and you can see this looks like a quadrupole scan. It looks like the beam envelope that I just presented on the other side. And if you plot the energy along the screen as a function of the beam size, you get, again, a fit which looks very similar to the ones I was showing before. The actual equation that you're using to fit to this quadratic is different, but the method is still the same. As I said, it's known as a butterfly scan. This is another example. So these are from the Wake experiment. The references are there, but you can see this is a measurement from the Wake spectrometer here. And this is the vertical beam size as a function of the energy. And they're able to measure the emittance. Another way that you can do it with plasma accelerators is with a pepper pot. It's single shot. And what you do is, single shot, that means bunch by bunch. You have a screen that you put into your beam, which is a series of pinholes or slits, and it breaks the beam up into beamlets. You let them drift by some distance, and then you image them. So the screens have come in again. Here's an example here. So you've got the beam without the screen in, and then the beam with the screen. You can see all these different spots. And then what you can do is you can plot the position of the spots as a function of how the beam was drifted from where you expect the spots to be if they had zero divergence. And you can build a phase space map. Then you can plot an ellipse, and the area of that ellipse, as I mentioned before, will be your emittance. So this is x against x prime, and then you've got an ellipse, and you're finding out the volume of that ellipse, not the area in the case of 2D. You can also calculate it directly from the image using some equations, but then you're looking at the properties of the individual spots. So how big is the spot? How much is it spread? How much is it moved from where it should be? So all these different parameters here are to do with the actual values related to the individual spots rather than just looking at the positions of them. There's pros and cons to the different methods. If you have a lot of spots, it's quite easy to do something like this, but if you only have a few, then it can be more beneficial to use this method. So what are the problems with it? So as an example of a pepper pot, this is a slit version, but you can imagine for a pinhole version, it would just be, it would look like the end of a pepper pot, which is where it gets its name from. The problems here are that it can be quite complex to make these measurements. You need to make sure that the beam is passing through this collimated as possible. They tend to be limited to the millimeter millirad range because of the properties of the screens. They are difficult to manufacture. You know, you're asking for what often relatively thick pieces of something like tungsten, very thin, small holes to be punched into it. So there's things like water jets and stuff being used to manufacture these, which they themselves are not very accurate in terms of keeping the line straight and things like that. So they're very difficult to manufacture. Apertures and the thickness of it, and they do tend to be limited to lower energy. So this might be something that you would apply to your witness beam before it is accelerated, or if you're not accelerating by much, if you have a specific application in mind and you only need a few MeV of beam, then this might be something you could use. But essentially, the idea here is that the beam passes through the holes and it doesn't pass through the mass of the screen. As soon as you start getting a higher energy, you're getting the beam scattered through the material rather than blocked, which means that rather than getting a nice pepper pot image with nice resolvable spots, you have this really high flat background of scattered beam. So if we want to do this non-invasively, how do we do it? And one of the things that people are looking at, myself included, is to do an optical version of this. So rather than measuring the phase space directly of the beam, we do this process of mapping the beam properties onto the optical properties, and we measure the optical phase space. If we can use a radiation source, which is non-invasive to produce this optical radiation, then that means the diagnostic itself is non-invasive. The beam goes past, it produces this radiation, and it carries on to its application, and then we do all the measurements on the radiation. The types of radiation which map the spatial and angular properties, the divergence resolution on those types of radiation tend to increase with energy, which is a bonus for us really, because we are targeting these higher energies. So the more you go to push into the GeV level, the easier this measurement becomes in theory. So how do we do this? Well, we either use mirrors or we use lenses. So on the left here is a device called a digital micromirror device, or a DMD. And this central portion here is an array of micrometer scale mirrors. Each one's individually controllable to 2 rotation states. And you can basically apply a mask to the image. So you can see it to the mirrors, sorry. And you can see here in the image that you've got these 3 black dots. They are a group of pixels which have been rotated to send the light away from the camera which is taking this image. So you can apply a mask to this, so like a pinhole or a slit, and move it around and sample the optical radiation at different positions. The problem with this is that it is multi-shot, but it means that because you have ultimate control on this mask, you really have whatever resolution you want. So this is an example of a monitor having some downside relative to a measurement, but you live with that because it is a monitor. So you need multiple shots here, but we make do. Here is an example of a lens array. So these lenses are, they have a pitch of 150 micrometers. So this is very small. This whole thing here is about 10 millimeters wide. And this has the benefit that it is single shot. The radiation comes through and each one of these lenses focuses the light which goes through it to its focal plane. And that means that you get a measurement of the angular distribution which is mapped to the spatial positions of the lenses, which again, you're mapping angular onto spatial, you're getting towards this correlation term and the emittance. Here's an example of a lens array setup. So you have a lens here at the start. This is your imaging lens. So you have your radiation source off to the right hand side here. It comes through and it's imaged. It brings the profile of the beam into focus on the lens array surface, and then the focal plane of that lens array surface is then re-imaged onto the camera. We also use like a beam splitter. It's called a pellicle beam splitter. It's basically like a 2 micrometer thick mica film, and it means we can extract some percentage of the light and send it through to a camera which is just looking at the spatial distribution. So we can use it for standard quadrupole scans and things like that as well. It also means we can check what the profile looks like on the lens array. So we've recently been to Clear to do some measurements with this. So there's an example of the chamber that we use. You can see in the center here, this is a transition radiation mirror. Transition radiation is, for this particular application, is not non-invasive, but the idea is that you can develop proof of concept type instrumentation with transition radiation, which is relatively simple to put in place and to simulate and things like this. And then once that's working, you can transition to a different type of radiation, which something like synchrotron radiation, which is what we're actually doing at the moment. And you then get your non-invasive element of that diagnostic. Here's a picture of the latest setup that we have in place. You can see it looks very similar to the one I've just shown. So the chamber here is this chamber. We have a periscope which brings the light down into our imaging lens, and then it comes through to where the lens array is and onto this nicer camera. And then we have this camera here, which is looking at the spatial distribution. And yeah, so that's the optical path that is taken there. And we were actually pulling off something like 8% of the light here and sending 92% through to the camera. So this is what it looks like when you do this sort of measurements. So you can see this looks very much like the pepper pot measurement I showed earlier, but this is individual spots of transition radiation. And this is what's happening as we pass the beam. We're basically doing a quadrupole scan on the transition radiation mirror, and we're taking a measurement for each point. So in theory, what we should be able to do is pull out emittance measurement for each point of the quadrupole scan, and then the quadrupole scan should give us a benchmark emittance measurement. If you plot out the phase space, as I showed earlier with the pepper pot, you can see how it turns over as we expect as it goes through the waste. So yeah, this is looking very promising. And this is sort of an area of active research for our group, at least. And then the final thing I'd like to cover is something called betatron radiation. So electrons traveling through an ion channel or a plasma bubble or whatever, however you're calling your plasma acceleration, they'll undergo something called betatron oscillations. So these are very similar to how a beam would be wiggled as it goes through an undulator or a wiggler. But it's happening in the plasma channel, and it produces incoherent X-rays, and this is what's called betatron radiation. The spectrum is basically a sum of all the individual electrons, which means it's quite straightforward to simulate. So here's an example of a simulated path of a beam. So this is the an awake simulation. So this is the 10 meters of plasma. They have a rubidium plasma source, which is 10 meters long, and the beam is being oscillated up and down on the micrometer scale. And then this is the spectrum of the radiation which is produced. It has a characteristic critical frequency, which is what you'd expect for things like fell radiation. So it's all sort of similar physics. But yeah, so we're measuring the spectra. That's the end goal, to measure the spectra. And then the idea is that you have independent measurements of the divergence and the energy. So you can do that very simply with a standard screen, and you can infer the normalized emittance from the spectrum of the betatron radiation. So here's an example here of a laser Wakefield version. So the laser's coming into a gas jet here. You've got this plasma bubble. You've got the oscillation of the witness electrons, and they're producing these X-rays. You then get the electrons out of the way with your standard spectrometer dipole onto the spectrometer screen. and the electrons, the X-rays, which were co-propagating with the electrons, goes through here, and you image them, and you can produce very nice measurements of the divergence in the spectrum and things like that. So, onto longitudinal profile. How you measure this really does depend on how long the bunch is, which is sort of a cheat, because what we're saying is we need to know how big your beam, how long your beam is before we can tell you how long the beam is. So normally what happens is this is guided by simulations, because invariably you'd know how big your beam is from before you start to build it. If the beam is longer than a picosecond or 0.3 millimeters, you use a street camera. These are so well made nowadays that you can just buy them off the shelf and attach them to your accelerator, and there really is no real R&D going into bunch lengths longer than this, because the street cameras work so well. Less than a picosecond, and then you've got this whole zoo of different techniques that are being developed, from spectrometry and interferometry, which is what I'm going to cover today. Also transverse deflecting cavities and electro-optical, I'll cover those as well. I'll touch on to dielectric structures as well. So just to give you an idea of what the street camera does, because they do have applications in plasma accelerators, they're just not the main thing we would look at for longitudinal profile measurements. The idea is that you have some radiation source. Typically these have been developed for synchrotrons, so it's synchrotron light that's being used. It goes through a slit, impinges upon a photocathode, which produces electrons, and then you pass it through this tube where there's a swept electrode, and back onto a phosphor screen to produce more light. And then you basically map the longitudinal profile, so you can see this one at the front here is up at the top, and one at the back is up at the bottom. So that rather than X and Y, you've now got X, slip, and T at the time. The absolute highest resolution that's been achieved is 200 femtoseconds, but I'd say there's like 2 cameras, maybe 1 camera on the market that can do this. Generally, they're all worse than this, because that's not what they've been designed for. However, they do have the uses, as I've said. This is an example from Awake. At the top here, we have the proton bunch, which is used as the driver there. You can see it's tens of picoseconds long, hundreds of picoseconds long, sorry. But then you go through the self-modulation process that Awake relies upon, and you can see these microbunches start to appear. And the street camera works great for this. You wouldn't be able to use any of the other diagnostics on the previous slide to do any of these sort of measurements. So the street camera really does sort of tell the Awake operators that the proton beam is behaving as it should before you start then accelerating with it. The resolution of these is fundamentally limited by the time dispersion of the photoelectrons. So that's how the timing jitter basically in the photoelectrons, they won't all be released from the photocathode with the same energy. They won't release at the same time, and they may go through slight perturbations in the electric field as it goes through the tube. So they won't all arrive when they should arrive. You also have space charge effects in the photoelectrons, so they'll actually spread out as they propagate. And then you have timing jitter. You know, if your beam is not if your beam has timing jitter on the order of the bunch length that you're trying to measure, then it makes it very difficult to stack the images together. The gold standard for these short bunch lengths and how it's used in the majority of accelerators with these sort of parameters is a transverse deflecting cavity. Everyone seems to have their own acronym for it. You can have a TDS, TDC, RF deflector, all sorts of things, but they're all talking about the same sort of thing. And it's basically an RF cavity which is used to excite a transverse mode rather than a longitudinal mode. So what that means is that your electron bunch comes in, goes through the cavity, and the RF field in the cavity kicks the head up and kicks the tail down. And it means that if you then propagate for some distance to let this kick to actually affect the bunch, you turn the longitudinal profile into a transverse profile. here is an example of some measurements we took recently at Max 4 with the TDC. You can see what we're doing here is a phase scan, so we're actually changing the compression that we're applying to the bunch. The bunches come through at different bunch lengths and with different energy spreads as well. And you can see how it's varying. So along here, so this is longitudinal phase space. It's the time against the energy spread. So if you sum the vertical direction, you get the transverse, the longitudinal profile. And if you sum the horizontal, you get the energy spread. And that works very well. Main problem with these things is they're extremely expensive, and the shorter the bunch length is that you're trying to measure, the more expensive they get. They are an RF cavity at the end of the day, so the RF cavity itself is expensive, the RF source is expensive, all the waveguides, they're expensive to run. There are various pieces of work ongoing to try and produce passive versions of these which don't require the RF source. So this is dielectric streakers. So here you have two metal plates which are 200 millimeters long, aligned with some dielectric, and as the bunch goes through, the head of the bunch will induce a field in the dielectric, which will then affect the tail. So the actual bunch is kicking itself. It's a transverse weight field, and you can get the same sort of measurements with this. This is work that's been done at Clara. Again, the references are there, but they are destructive to the beam. There's no way of getting around that. And that means that you can't do online monitoring. You can't send the beam through this and then through to an undulator because it just won't radiate. There are plenty of pieces of work ongoing where you have this measurement after the beam application. So you send your beam through your undulators, you then keep the beam out of the way to send the X-rays on the way to the users, and before the beam goes through the dump, you pass it through a TDC. That means that the beam has been changed by whatever process it's gone through. But if you have some way of back propagating through that process, so maybe you also monitor the X-rays in the undulator scenario, then you can do that back propagation, but it is complicated and it is application specific. For non-invasive methods, invariably they're all trying to reproduce something called a bunch form factor, and that is a Fourier transform of the longitudinal profile. So here's an example of 4 different bunches, Gaussian bunches, I should emphasize. And you can see that for the shorter the bunch, the higher the frequency content of the bunch, which means that they have higher contributions of the different frequency bands. So yeah, it's a Fourier transform. Spectroscopy works by sampling this form factor directly. So you'll say, like, what's the intensity of the radiation that's being produced at 7 terahertz, at 6, at 5, and you basically plot out the form factor. For interferometry, you're looking at correlation methods to try and basically infer what the structure looks like. In both of these, you will be fitting the tails of the distribution because you can sample the full distribution. There's certain higher frequencies, there's certain bands which are absorbed by air or various other materials. You'll have absorption throughout your entire optical system. The different materials will absorb some different bandwidths. And then you'll have the very low frequency stuff, like certain gigahertz, you just can't get out of the beam pipe because they are interacting themselves with the beam pipe because of the size of the wavelength of that frequency. So spectroscopy, so the gold standard, the best spectrometer that we've seen so far in the community is this one here. Again, the reference is there. And what makes this so special is it's multiple spectrometers tied together. So the radiation comes in through this hole here, and it's its first grating, and the grating sends a certain bandwidth of radiation off to a detector and sends the rest of the radiation on its way. And it does that repeatedly, and each grating looks at a different bandwidth. And you can see this is an example of what one of these gratings and sensors look like. You've got this line array of detectors, so you can see that you've got different frequencies here, and the different detectors are sampling the intensity at that frequency. That means you can literally plot out the form factor. So this is more of a realistic bunch, that's why it doesn't look as smooth as the one I just presented on the previous slide. But you can see they're extrapolating here at the low frequency end, as I said. But it means that you can then work backwards and get back to the profile. So they're on deflected cavity of TDS here, but that's what it means. So that's almost like the ground truth, the gray curve in these two examples. And then they have two different methods of analyzing this, the spectrum. And you can see they're basically agreeing with what the TDC says, which means that this is a non-invasive method of taking this measurement. There's not been a huge uptake of this because of the complexity of the system. But what it has caused is a lot of people to look at, can we sample like a subsection of this and still produce a similar result? So measurements done at SLAC here, they're using virtual diagnostics. And what they have is their accelerator, and then they have the spectrometer being using non-invasive radiation. Well, actually here they're using CTR, but they also do non-invasive radiation as well. And they send this through a prism, which is specifically for the infrared, and they're sampling the infrared. This is a stylized version of where it is. This is not where it looks like. It's a much shorter frequency range than this. It goes through, say, different applications. It's an undulator set up with different parameters, and then they have this deflecting cavity after the undulator, and they can train a model to say, given the spectrometer, this is what longitudinal phase space looks like, and it means that when they turn off they start running the beam through the undulator, they still get the spectrum, and the model can infer back to what the longitudinal phase space looks like. Virtual diagnostics are being used a lot in a lot of these applications nowadays. I've not really touched upon them too much because it would have doubled the length of this seminar. This is really the hardware required to run these sort of diagnostics. So then moving on to interferometry. The interferometers don't look too dissimilar to an interferometer you would have probably done at undergrad. You have some radiation source, it comes through, it goes through a beam splitter, you have a fixed mirror and you have a movable mirror, and then you have detectors, and you use those detectors as you move the movable mirror, and you build an interferogram, use a Fourier transform, and you get back to the form factor, and then if you can reconstruct the phase, you can get back to the bunch length. As I've said here, so they only actually sampled between these two lines, then they had to fill the high end and the low end with some model, but they actually tried this with two different radiation sources. So CTR's got coherent transition radiation, and then use something called coherent Cherenkov diffraction radiation, which is non-invasive for this application. And you can see you got very good agreement. This lower end tail stuff, this is probably coming from the reconstruction at the low frequency end, but the actual main properties of the bunch have been reconstructed very well, and it offers a lot of self-consistency. Electro-optical sampling. Electro-optical sampling makes use of something called the Packel's effect, and that means in certain materials, if you apply an electric field, it changes the refractive index. Whoops. Onto sneak preview of the end slides. There we go. It changes the refractive index of the crystal as the bunch goes past. The electric field of the bunch changes the refractive index of the crystal, which means if you have some sort of laser pulse going through the crystal at the same time, you can encode the longitudinal properties of the electric field in the bunch, which is the longitudinal properties of the bunch itself, onto the laser pulse. And then if you can decode it from the laser pulse, you've got a non-invasive diagnostic. So yeah, you can see how the laser pulse is propagating from left to right, and how the birefringence is changing as the bunch goes past. Here's an example of an experimental result. You can see it works very well, but you can see the sort of timescale that this is working on. It's working for the sort of sub 100 femtoseconds range, but it's mainly limited by resonances in the crystals. So it's limited by the actual electro-optical crystals themselves. GAP is currently the best one. It has a resolution of around 54 femtoseconds. So it means it's really limiting what you can do in terms of like the laser wake field stuff, where you get into like sub femtoseconds. But there is an active research area where we're looking at metamaterials, spintronics, things like this, which is going to push the resolution of these things down to the femtosecond scale. So with that, I've come to the end of my slides. Yeah, so I'll be happy to take any of your questions. Just for the sake of the video, there is the references if anyone's interested. I'm sorry you can't click on the links. But yeah, thank you.
Thank you very much for that, Joe. So we have got a couple of questions for you. And if anyone else thinks of any whilst Joe's going through these answers, then please feel free to put them in the Q&A and we'll put those to Joe. So first of all, could you explain to us, could virtual diagnostics ever fully replace physical measurements in the future?
So as I mentioned, like virtual diagnostics, they're super interesting, and there's a lot of work in this area at the minute. Machine learning is sort of impacting everything with accelerators at the moment. The reason I didn't cover them more directly, as I said, is because I could have talked for another couple of hours about virtual diagnostics by themselves. I don't think they're ever going to completely replace normal diagnostics. They will always be complementary. The problem is that you need the standard diagnostics to deliver the data to train the virtual diagnostics. And what we need to think about is that if we can come up with new types of novel hardware, new types of novel measurements, we can come up with new types of novel virtual diagnostics. Some of the virtual diagnostics that we have nowadays are limited by the underlying physical measurement process. So that's really what we should be targeting, this combination of hardware and software. We're never going to just have one of these things, and they need to come together.
Thank you very much. We've got a couple more questions. So first of all, what method would you use for electron beams with Poynting jitter?
Poynting jitter. So that would be like the transverse position that I was talking about. It really depends on what sort of thing you would be looking to measure. So just for transverse position, we use something called a beam position monitor, and it's sort of super creative with the names of these things. It is what it says on the tin. It measures the position of the beam transversely. So you would have some sort of button or strip line in the beam line, and the electric field from the bunch gives a signal on the buttons, and the difference in the signal gives you a relative distance between the buttons, and you can measure relative to the center of the beam pipe. Otherwise, for jitter, it doesn't really impact things like profile measurements, because you can always pull the profile even if it's moving around the screen. If I go back a couple of slides, to where I was showing the TDC images. Sorry, far too many animations. Here we go. Yes, this has been extremely well cleaned up by my PhD student. You can see a clue here. You see these lines that are appearing in the corners of the distribution. These are the sort of resolution measurement lines on the screen that we've been clipping out because they interfere with the measurement. They give a clue. The beam is jumping all over the place here. But what we can do is we can find a centroid and center it. So it really doesn't impact on many things. It's just the actual position. If you're trying to align it into a gas jet, for example, or for a wake, I know that they need very good alignment between the proton beam, the laser, and the electron witness. The Poynting jitter has a big impact there, but it's really, in terms of anything else, it doesn't affect it too much.
Okay, thank you. And the next question, regarding virtual diagnostics, how is degeneracy handled? For example, for the case you showed, is it possible that two different longitudinal phase spaces give the same spectra used to train the neural network?
Well, as I mentioned with this form factor, it's the Fourier transform of the longitudinal profile. So if the longitudinal profile, so what you're actually saying is, are there multiple what they call it, different applications that can produce the same longitudinal profile. And there probably are, yes, but at the same time, that would produce the same spectrum, and that's probably okay because that's the measurement you're trying to take. Beyond that, yeah, then it's really just a standard machine learning problem in that the diagnostic itself will only work as well as the data that's been used to train it on. So you really need to make sure that the parameter space is well constrained, and you've thought about how you want to take these measurements. It's not just a case of like as I said before, there's no one fit to all problems. So yeah, you really need to think about the application and the specifics of the application.
Okay, thank you. And I've got one more question to read out. So if anyone else does have any questions, make sure you pop them in the Q&A right now. So the question is, why is it so much harder to measure transverse emittance in a plasma accelerator compared to a conventional LINAC?
There's several reasons. So as I mentioned, that the things like the PepperPot and the quadrupole scan, they rely on the beam being able to propagate in free space for some period of time before you take the measurement. So the PepperPot, once you've passed it through the screen, it then needs to propagate for some distance before you image it. For plasma accelerators, you get very strong focusing in the plasma. As soon as the beam leaves the plasma, it has a very high divergence and goes like this, which means that any sort of significant propagation distance and you're going to lose the beam. Also, the problems with the energy as well, the energy scans, energy spread, that's just an issue generally. The resolution limit as well, pushing to sub-micrometer level emittances, they're just very difficult to measure. The profile measurements become very difficult, the divergence measurements become very difficult. You actually start to become coherent at the optical radiations in some of these applications, which means that the profile that you measure is not the profile of the beam. It's been interfered with by the properties of the radiation source. So things like Betatron radiation and deflected structures really are the main ways to get around this. And then we've got all these new methods that are being produced.
Okay, thank you. And we've got another question. After the beams pass through the deflecting cavity, the shape of them seems to be changed. Does the beam quality change too? And can it still be used after the deflecting cavity?
No, you can't use the beam after it's been through the deflecting cavity. You've rotated it by 90 degrees along its axis, along its transverse axis. It means that something like a FEL where you would want very small transverse emittance, you've basically made the longitudinal profile the transverse profile, and it won't have very nice emittance anymore. This is what we mean by it being destructive. Sorry, what was the first part of the question? You said something about it looks like the profile's changing.
It says, after the beams pass through the deflecting cavity, the shape of them seems to be changed. Does the beam quality change too? And can it still be used after?
Yeah, so like I said, you can't use it after. The profile is changing because it's changing here because we're doing a scan. So each one of these images is a different set point in the scan. But you can imagine how this has been stretched in the wrong direction. That's why it looks like it's changing. But fundamentally, this is a good schematic. What I like about this is the colours. You can sort of follow where the different parts of the bunches have ended up as it goes through. But yeah, so basically you're kicking it around by 90 degrees. So it's just not usable afterwards.
Okay. Oh, we have one more question that's just come in. So if a beam has low energy tail, should we calculate the emittance for the high energy part or for the whole beam, including low energy tail? How can we characterize the beam in this case?
We could have a whole philosophical discussion about what emittance actually means. That is a thread that you don't want to pull on. Yeah, it's a good question, and there's no real right answer to it. It's just you need to know why you're measuring the emittance and what is important. Is it that the high energy section is the main section that's important for your application? Then that's the emittance that's important. If the full beam is important, then you need to look at the full beam. Typically, if you have a high energy spread, I've not mentioned it here, but you would look at something called the slice emittance. So this would be how the emittance changes, because the emittance is a transverse property, how the emittance changes at different longitudinal positions along the bunch. So that would probably capture the sort of thing you're talking about, where you have a low energy tail, you would pass it through a deflecting cavity, and you could look at how the emittance changes up longitudinal profile.
Okay, that's brilliant. So thank you very much to Dr. Joseph Wolfenden from the Quasar Group at the University of Liverpool for his seminar and for answering all of those questions. Thank you. For your information, we are going to take a short pause from the Eupraxia seminar series over the summer period, and we'll be back in the autumn time. So look out for emails from me about the next seminars that you'll be able to book onto. We'll send you more details of the speakers and the topics in a couple of months' time. So thanks very much for attending, and thanks very much again to Joe. I hope you all have a nice Friday and see you soon.